So for this one, cross multiply the 3 to the 6r minus 5 and the negative 1 to the 9r minus 3. When there's a group, you have to put parentheses or you will do it incorrect. So my next step here then, once I have it set up, is to do what? What do I need to do here? Distribute, right? So I'm going to say 3 times 6r. What is that? 18r. 3 times negative 5. What is that? There we go. On the other side, a negative 1 times a positive 9r is a negative 9r. What about this one? Negative 1 times negative 3. Right, so we're going to say plus 3 there. All right. Once I have the distribution done, I need to move what? What do I need to do here? Variables to one side, numbers to the other. Yes? All right. So I'm going to move my variables to one side. So if I move my variables over here, then I'm going to move my numbers to the other side. Your numbers should cancel on one side. Your variables should cancel on the other. All right, numbers cancel on one side, variables on the other. 18 and 9, what do I get there? 27r. On the other side, I have 3 and 15. I have one final step here before I simplify. What do I need to do? Yeah, I need to divide both sides by that 27. Both sides divided by that 27. So I end up with r equals 18 over 27. Am I done? No. If your fraction can simplify, you need to simplify. What goes into 18 and into 27? 9. Yes. So we're going to divide the top and the bottom by 9, which is where we're going to get our 2/3 as our answer. So Fibonacci had these sequence of numbers. B is actually his. But let's just talk about what sequence of numbers are. A sequence of numbers is when you have a pattern of numbers. And so when you look at patterns of numbers, you say, well, how do I get from 3 to 4, and then 4 to 7, and then 7 to 11, and 11 to 18, and then you figure out what the next one is. And so Fibonacci's is one of the more famous ones. His is this second one here. And so you look for a pattern to see, how do I get to the next number? For this one, our first two numbers are 1 and 1, and then our third number is 2, and then our fourth number is 3, and then our fifth number is 5, then 8, then 13. How are they getting from one number to the next? Any takers on that? So if I look at this, 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, 5 and 8 is 13. What's my next number going to be then? It's 21. Then what's my next number going to be? 34, and so on and so forth, okay? And that is Fibonacci sequence. What he found was, he started looking around and he was like, hey, a lot of things actually do this pattern when they are growing. Natural things in the world have this pattern. And so if you take this pattern and you create these rectangles, I'll show you what they did. You have, these are 1 by 1 squares. So they took this rectangle, they divided it. 1 by 1 square, and then a 2 by 2 square, and then a 3 by 3 square, and a 5 by 5 square. You get the picture. They're using these squares based on this pattern. And then if they draw this spiral through the squares, just as they arc through the outside corner of the square, you get the Fibonacci spiral. It's also called the golden spiral, all right? And so then from there, they looked at what's called the golden ratio. As you travel through these numbers, you have a ratio between them that starts to appear. You don't see it as much here. 2 over 1 is like 1.5, 3 over 2, or 2 over 1 is 2. Then you get to these 1.5, and then you get, but as you get further, you get this ratio that is a 1.619, and it goes on a little bit, to 1. So a unit rate here, as I keep going through this, is a 1.619 to 1. Now, what we started finding as they started looking at Fibonacci's ratio and looking at this is called the golden ratio, and looking at the golden spiral, it is amazing where you find this in creation. It is literally everywhere. And so we're going to watch a quick clip on this sequence that moves us to this particular ratio. So we've been talking about ratios and how things go together with ratios. We're about to use ratios for similar figures. And this is almost like, if you've heard the term tessellation, a pattern of repeated pictures, so to speak, that the pattern is created in this ratio. Is that this ratio here is found, as they showed, even in the human body. the ratio between your finger segments, the curvature of the human ear, it follows the same pattern. And so it's not like it's just in plants. As you saw, even the waves of the ocean, you will see this particular spiral. So it's really, I mean, one of my favorites here is to study just the history of this and when he discovered the sequence. And then from there, it was as if everybody started seeing it. They're like, oh, wait, now I see the pattern. Once he discovered the pattern, they started realizing how in depth and how far it spread. There wasn't until we had capability to even see the galaxies that we would have known that this spiral was also in the galaxies. So very interesting. Just now in the video, we saw what is almost like similar patterns. It is a repeated pattern in that particular sequence. And so while the pattern gets larger, they are similar. And by similar, we mean that they look the same, but they're different sizes. So if you turn to page 105 in your books, we'll actually look at the term similar. We saw similar figures in the video, and by definition, similar figures have the same shape, but not necessarily the same size. And so if they have the same shape, meaning all the sides are exactly equal, but they're just different sizes as far as the actual length, what we're talking about is the ratio between the sizes. So the ratio between the sizes will be the same. The ratio between the side lengths will be the same. And so similar polygons have corresponding angles that are congruent to corresponding sides, which are proportional. And so notation, the first thing I want you to know about similar figures is the notation here. The notation looks like this little curve. On a keyboard, it's like in the top left corner there. It is also used with congruence, but with an equal sign. So similar means they're not congruent. They look the same. They're different sizes. Similar figures. Your angles in similar figures will be exactly the same. So then this little mark right here looks kind of like the similarity, but with the equal means congruent. So that means angle A is the exact same angle as angle X, C is exactly Z, and B is exactly Y. Order is important. They put A first here. That means the angle that corresponds to A must be first here. If they put B second, then that means the angle that corresponds to B must be there. And if they put C here, then the angle that corresponds to C must be there. What I want you to notice is this word proportional. All right? While the angles are the same, the sides are proportional. The sides are proportional, meaning they have the same ratio. So if you know two of the sides, you can solve for another side in a similar figure by setting up ratios and using cross multiplication, which is what we've been doing, all right? And so we're going to look at the first example. Now I will tell you, so they have find x, y given the measurement of two similar triangles. So the key word here is they told you that they are similar. If you know they're similar, then you know their sides will be proportional, or they will be equal fractions. And so if you know that, then you can set up proportional sides and angles here. So let's look at this. So they've labeled this first one A, B, and C. And they've labeled the second one X, Y, and Z. And so they've told us that they're similar. So we're going to say triangle ABC is similar to triangle X, Y, and Z. All right? When they tell you that, then they are telling you that XZ, because that's in the same order, is proportional to A. Oh, I just switched it. I'm going to switch it down here to AB, and I wrote the wrong one there. So let me switch this. I'm going to do it differently than they did in the book, just because they used decimals. So we'll put AB there, C there. All right. So it's proportional to this guy here. All right. XZ is proportional to AB. All right. And they want us to find XY, all right? So what our rules tell us is I should be able to set up a fraction between this one and the one I don't know and solve it. They should be equal. They should be proportional. So the way I'm going to do this is I'm going to say 5 over 10 should equal m over 27. All right? Now, when you're doing these, if you can reduce one, you can do it. So if you can reduce a fraction, it is equivalent to the fraction that you currently have. So when I'm looking at this, before I start cross multiplying, while you can say 5 times 27 equals 10 times m. That's certainly fine to do that. But 5 times 27 is a much larger multiplication. So what I would rather do is I would rather reduce this first. And then I have a much smaller multiplication going on, right? So what can I reduce 5/10 to? 1/2. So now I can write it like this. Much simpler multiplication, obviously. 1 times 27, that's just 27, equals 2 times m. And then I have a very simple way to figure out that side length. I just divide by 2. So m is going to equal what? 13.5. 13.5. All right? So if I have similar figures, if they have told me they are similar, then I can set up a proportion. 2 fractions equal to each other and cross multiply. The only thing here is you have to do it in the same order, okay? You have to do it in the same order. If I put the 5 over the 10, then I must put the m over the 27. I have to, okay? If I switch it, I will get the wrong one. Now, you could have started and put 10 over 5 and then 27 over m, but whatever order you do it in, you need to stay with that order. My recommendation is that you always start with the smallest figure, and that's your numerator, and then use the larger figure as your denominator. That way you never confuse which is on top and which is on bottom, all right? But as long as you stay in the same order, you'll get the answer. So you have to make sure that if you start with this one on top, then the other one from that same triangle needs to be on top, all right? All right, so same triangles as before, except I filled in the other sides. 5 compared to 10, 13 compared to 27, and then 15.5 compared to 31. Those are all in a 1-to-2 ratio. Everybody agree? Those are all 1-to-2, and that's how this should work if they're similar. If they are similar, I should be able to put every single one of these on top of each other, and they will equal the same exact fraction. And so if I were to reduce all of these, every one of those will reduce to 1-to-2. If I write 31 there, 1-to-2, okay? They should all reduce 1-to-2, which is how it should be. And so now what they want to do is they want me to compare the ratio of the perimeters. So what's my rule for perimeters? How do I find perimeter? You just add them up. So the perimeter of the smaller one, the x, y, and z one. So the smaller one perimeter is going to equal 5 plus 13.5 plus 15.5. All right? What do I get there? So 5 and 15 is 20, plus 13 is 33, plus one more is 34, right? What about my perimeter, my larger one? I get 10 plus 27 plus 31. What do I get there? Yeah, I get 68. And so what is the ratio between my two perimeters?
1-2.
Yeah, and so you'll see that even the perimeters do the same ratio. All right, so even the perimeters do the same ratio. If the side lengths are in a 1-to-2 ratio, your perimeters will also be in a 1-to-2 ratio. All right? So I'd like you to try one. Go to page 109 in your books. And I want you to try number 4. Number 4. You are going to get a decimal. I started with 10 over 32 because that's the only two that I had both of, right? I didn't have both of these. I had an A there. I didn't have both of these. I had a B there. So I started with these two sides, 10 over 32, and I reduced it. Then I took the 5 over 16 and set it equal to the 15 over A and cross-multiplied and solved. Then I took the 5 over 16 again and set it equal to the 17 over B, cross-multiplied and solved. Okay?
Do you have to do the 6?
It says find the height of a flagpole at the Parliament House in Canberra, Australia, if it casts a shadow of 106 feet on level ground. At the same time that Sydney, who is 5 feet tall, that's supposed to be 5, not 5 inches, cast a shadow that is 2 feet on level ground. All right? Now, when you have a word problem like this, what they're basically doing is they're giving you two triangles. They're giving you a small triangle. So Sydney is 5 feet tall, and she cast a shadow that is 2 feet. All right, and so that's going to create this triangle here. If it'll draw it for me, that would be great. It's going to create this triangle. Nope, it's not going to draw me a triangle. Sydney is 5 feet tall. That's 5. Her shadow, well, where's her shadow going to be? Right there, okay? She's 5 feet tall. Then we have this flagpole here. We don't know how tall he is. Beautiful triangle there. So we're trying to find out how tall, find the height. But we do know how long the shadow is for that one. That's what? 106, right? And so this should be the same exact ratio, all right? I should have something like, and we can actually do, you can do 5 over 2 and x over 106, or you can say 2 over 106 and 5 over x. Either ratio is fine. 2 over 106 is going to reduce, though, equals 5 over x. Now, my point here is that if I put 2 on top and 106 on bottom, then the 5 must be on top and the x must be on bottom, all right? Whatever order you start with, you have to do that the whole time. Got it because I divided wrong. 1 over 53. Is that better? 5 over x. Yes, you only have to reduce one of them. You don't have to reduce both of them. This is 265. Hopefully. Right, I reduced wrong. Nobody caught me except Mikey. If we're doing this, I would put this smaller triangle on the numerator side. The biggest problem I have when people do these is they switch. So they'll say 2 over 106 equals x over 5. And they just switched it. All right? And so if you always put the smaller figure on top and the larger figure on bottom, then you're going to be fine, right? You're going to keep it the same. But if you don't pay attention to the order you do it in, it's going to be wrong. You could have said 106 over 2 equals x over 5. You're going to get the same exact answer, all right? But if you flip-flop around what you're doing, then you'll accidentally switch them in the same problem, meaning you'll put one correctly and one you'll flip the other way. And so if you always do the smaller figure on top, it usually keeps you from getting confused, all right? As is, this creates a way to do a scale model, all right? So what Sydney represented here, she was a scale model of the tower, or the tower itself, the flagpole. And so because they were similar, if you've ever been to like a museum that had a scale model of something, if it is truly to scale, then that means every single inch of that model corresponds directly to the actual size of the object that you're doing a scale of. If you've ever worked with like scale model cars, if it's a true scale model, then every piece of the car is going to be in the same ratio as the actual car itself, okay? And that's what this is doing. So look at the next example of a drawing or model is the ratio of the dimensions of the drawing or model to the corresponding dimension of the actual object. In a scale drawing, all the dimensions are the same scale or ratio, all right? So we're actually doing one from the work part of this book, not the example itself. The distance between Nashville and Knoxville is about 160 miles. How far apart are the cities on a map that has a scale of 1 to 10? All right, so if it's a 1 to 10 scale and they're actually 160 miles apart, how far apart are they on the map? Well, it's a ratio. 1 to 10, that's 1 inch to 10 miles equals how many inches to 160 miles? There's two ways to do this. Cross multiplication is what we've been doing. What's another way to do this? When it's just a 1 on top, it's really easy, especially when they're divisible. How do I get from here to here? You multiply by 16, right? So I should be able to multiply from here to here by 16 and get equivalent fractions. Think about when you're reducing a fraction. When you're reducing a fraction, you're dividing by the same number, right? When you are finding your scales and your images like this for scale modeling and scale drawing, you're really just multiplying both numbers or dividing, depending on which way you're going. It works that way, and it works with cross multiplication. 1 over 10 equals x over 160. Cross multiply. 160 equals 10x. X equals 16. All right, so when you're talking about equivalent fractions, cross multiplication works. And if it is evenly divisible or evenly multiplied, then that also works.